In the past, controlling robots has entirely depended on what kind of messages we can send the robot and what kind of user interfaces we've built to interact with them, which doesn't provide a lot of flexibility. By using large language models, or LLMs, and providing them with a few tools that can control robots, we gain a lot more flexibility. We can issue natural language commands to the LLM, which then works out how to break that down into subtasks and send them to the robot. In this video, I'll show a demonstration project of controlling a simulated robot using an LLM called Claude by Anthropic, which is based in the cloud. I'll show you the demonstration, show you how to set up the demonstration, and then walk through the code to show how exactly we provide these tools to the LLM so that it can control our robots for us. But first, this demo project wasn't made by me. It was built as part of a robotics course from the Zurich University of Applied Sciences. There's a few people I'd like to thank, so please take a look at the description if you'd like to see who built the course and who's responsible for the exact demo project that I'll be using. With that, let's talk about why we'd want to use LLMs to control our robots. Large language models, or LLMs, are artificial intelligence models that perform really well at understanding human natural language and our intentions. While the way they work is simple, just predicting one word after the previous word, the behavior we get can get really complex. They can even generate entire books and essays. That means using one to control a robot comes with a few different benefits. First, we can express high-level actions in natural language. You can tell a robot to go and make a cup of tea if it has enough tools built into it to know how to do that. Because we don't need to tell it every single step, it really simplifies our way of interacting with the robot. Second, using an LLM allows us to add extra tools into the LLM. For example, instead of telling us to move a robot a fixed distance forward, we can tell it to move forwards for a fixed amount of time. And because the LLM can control when that command starts and when that command stops, we've gained extra functionality from our robot that is provided by the LLM. Of course, that depends on the capabilities of the LLM. Third, as mentioned with a high-level action, LLMs are good at understanding what subtasks are needed to make up an overall task. So if you did want to make a cup of tea, it would know that it needs to move to the cupboard and then open the cupboard and then pull out the tea bags, for example. And finally, number 4, they can give human-readable responses to our requests. So if we did request something from a robot, the LLM will reply what it asked the robot to do and what kind of feedback it got from the robot. We can even ask it to summarize data it's received from the robot. So if we ask it to listen to a velocity topic, it will tell us what kind of messages were sent on that topic and what that made the robot do. That means we get high-level feedback to what our robot is doing, as well as being able to issue high-level commands. Unfortunately, LLMs are computationally really expensive. They're normally only deployed to large servers or data centers, and running one on a robot is practically impossible. Therefore, what we have to do is connect to the cloud to be able to use an LLM. That comes with its own drawbacks. It means our robot can only use the LLM when it's got a reliable internet connection, and using the cloud comes with its own host of pros and cons. Take a look at my blog post in the description if you want to read more about it. Assuming our robot does have a reliable network connection, we can use the LLM to augment what it's able to do and improve our communication with the robot. So let's take a look at what kind of commands we can issue to Claude in order to control our simulated robot. Here we are streaming from my laptop, which is a Linux laptop with a GPU behind it. Now, it's up to you whether you run the simulation on a Linux-based machine or on Windows. What I found is that on my Windows machine with WSL2, it's not able to give the GPU access to the Docker container that the simulation runs in, which means it runs really, really slowly. So for this demonstration, I'll be streaming from the Linux laptop, which does have the GPU pass-through, and so the simulation is much more smooth. So what we have here is the gazebo simulation with a small room or small house. This is available from AWS and has had some tweaks. There's more information in the repository in the description if you want to know more about what's happened. But through this simulation, we can actually see the robot moving around, and here is the robot in the middle here. We've also got this RViz window, and I've closed this down to just the map that's being shown of the robot. So we'll see that there's currently nothing, and that's because the simulation is paused. And finally, this window here shows the opportunity to give Claude an instruction or a request. So let's start the simulation and see the map start to build up. Here we can see SLAM in action. The front LiDAR of the robot has been scanning around the robot and has identified a lot of the walls that we can see in the simulation. It's also started to see the sofa. So from here, what we could do is using our normal nav2 goals, we can start to move the robot around. That's a very fixed way of doing things. What we can instead do is use the LLM to control it. So let's start with something simple. We're just going to move the robot backwards. And we can be a bit vague about our instruction. So we could say a meter, or we could say a yard, and ROS2 works in meters, so the LLM has to translate yards into meters. And here we can see the robot moved back a bit before then straightening back up again. And if we look at the LLM's response, it says it sent the command to move backwards by approximately 1 yard, which is then translated into meters. It then gives the set of instructions of what it did, set the X coordinate, set the Y coordinate, and set the orientation back so that it straightens up. And then it's got a last line of a bit of a summary. So that's given us a lot of response. It's done an automatic translation of units for us. You can see the kind of flexibility you gain here rather than sending a specific message of move to a position set in meters. What else can we do? Well, that's a question not just for me, but for the LLM. What can you do? We ask the LLM, it sends the request off, and then after a few seconds, and it does take some time for these commands to be issued, then we should get a response. Currently, we have a save map called default. We can provide information about the ROS setup, including nodes, topics, and services. Or is there any specific capability you'd like to do? I'd like to know what tools you have available. What tools do you have available? And again, we wait a few seconds for this. And here we go. The response it gives us, it can give us information and diagnostics about ROS2. It can do navigation and movement, such as navigating to a position, navigating relative to the current position, or navigating to a location by name. It can do exploration and mapping, log management, mathematical operations, and a few other things. So I think one of the more interesting ones is going to a specific location. So let's send it to a location. What locations do you know? And here it tells us it's got 5 predefined locations. So I happen to know that the kitchen is here on the map, so let's send it here. Go to the kitchen. This is the kind of natural language command with a high level action that is then translated by the LLM into something the robot can do. In this case, it's not much of a breakdown because the navigation stack used by the robot is told to go to the specific location. So the LLM's action is very minimal, but we can queue up actions and do quite a lot more complex things with the LLM. We can see the robot has moved into the kitchen, and if we take a look at the map, not only can we see the line of where it's traveling, but we can see the map fill in as it moves around the map. So we know that as it moves around, it builds up the map, and we can use that. Now it's reached the kitchen. Let's tell it to explore the house. And now we can see, again, the lines where it's planning to travel, and it's navigating to the empty space on the map to figure out what's there. Now, we'll change the paths that it is planning while it's in motion. As it uncovers new parts of the map, it decides that it's more important to go to a different unknown part of the map instead of continuing on its previous path. So we do see those paths change. And here the robot has decided it's going to collide with the wall. It tries to figure out what to do, and this is part of the navigation stack itself. So it should figure out that it can't get through the gap and just stop where it is. This is our opportunity to try and free it with the LLM. Stop moving, move around the wall to your left. So here we go. Because we've issued stop moving, it cancelled the plan. It then got confused about how to move around the wall. So the LLM isn't flawless in its instructions, but you can see by the commands I'm giving that they're much higher level than I would give by sending a ROS2 message. So now that we've seen the simulation in action, let's take a look at how to set it up so that you can set it up for yourself if you would like to. Dependencies for building this project include Docker, which is listed here, and there'll be a link in the description, and the NVIDIA Container Toolkit. Now, this is required because what we're doing is running simulations and RViz in actual windows of their own. So to be able to display these windows outside of Docker, we need the Container Toolkit to pass through the graphics layer. That means that Docker can actually run Windows as if they're running on the host. You can follow the installation instructions for these 2 pages and make sure that's running correctly before proceeding with the rest of the setup. Here we are on GitHub. Now, this is the original project that was released. You can see that the README contains instructions for building it. And what the README guides you through doing is pulling the Docker image that this example is based on and then installing the extra dependencies. To make it simpler, I've forked this repository and added a Docker file to make the build simpler. So let's work through the instructions here. First, we want to set up a folder to put the Docker file in and an API key for connecting to Anthropic. So here we are in the command line. We are going to create the folder and change directory into it. Now, the first file that we want to create in here is the API key. And this is required to authenticate a connection with Claude so that it can respond to your requests. Because Claude isn't a free service to use, the API key has to be connected to your account with some credit on it. So it does cost money to make requests. Let's look at how to set that API key up and how to save it. If you navigate to console.anthropic.com, the link will be in the description, as well as my blog post that gives all of these instructions as well. You go to the console, create an account, and then work through to get API key. Now, this will give you the option to create a key. For me, I'm able to just create a key directly because I already have credit on my account. For you, it will prompt you at this point to add some kind of payment information. So add a card or however you'd like to pay. Once you've done that, you can add a key. So let's call this temp key. And remember that API keys can be used to connect to your account and spend your money. So they're really something that you need to keep safe. I'm going to show you because as soon as this is done, I'm going to revoke this API key. So from here, copy this key because once this window is closed, you won't be able to access the full API key again. So copy that key out. We're going to edit a file called apikey.txt. And inside this file, we're going to paste the key that we just copied from the website. Then we're going to save it. And that's our authentication that we need to connect to Claude. Next, we want the Docker file used to actually build the container. To get this, again, if you look at the README, there's a command you can use to directly download it from my GitHub. So if I paste this in, it will just download the file. And we can take a look at this. And just see, there's not a lot to it. It runs from a starter image, clones some stuff into it, sets some environment variables, and does an initial build. There's not too much here. So with that, let's actually build the image. Now, if you're running on WSL, like I am, and you run this command, this happens because Docker Desktop isn't running. So if you're running on pure Linux and you've got Docker installed correctly, this won't happen. For me, I just need to run Docker Desktop so that it has access to Docker. So let's attempt this command again. And this time it can start to build this image. So it will pull the base image from online, it will clone the code into it that it needs, and it will perform an initial build. And after about a minute and a half for me, this build is complete. I can now clear the screen and issue the run command to see it in action. Now there's 2 commands that I have available for this. They're both quite complicated because they have extra flags needed to pass the graphical layer through to Docker so that it can actually pop windows up and show things in it, like the simulation and like RViz. So for most machines, I would use this command. However, there's a second command if you are running a Linux-based machine that will pass the graphics card through, not just a simulated graphics layer. What I have here will run very slowly because it will use the CPU to render the simulation, and that's really slow. But if you can use the GPU to render the simulation, you'll see that it runs a lot faster and a lot smoother. For the sake of the build demonstration, I'll use this command. For your own command, it depends on what machine you use. And you can see it's starting to pop up some windows. We've got the underlying log that's coming from our container. We've got a simulation window, and we've got the RViz window. Now we've already seen these in action, so next I'm going to show you how to run the prompt that actually connects to Claude. For this, you need a new terminal. Now, we already have a container running the simulation, so we're actually going to connect to this container and run a different command inside it at the same time. By running this command, we should get the prompt come up. And here it says, enter your request. From here on, the demonstration is the same as I've already showed you. Press the play button to start the simulation, the map should start filling in, and you'll be able to issue your requests to the LLM. So that's how we set up the simulation, but how does the code underneath actually work? Let's take a look at how tools work using the Rosa library and the LangChain library from Python. Here we are in VS Code. What I've done is used Git to check out the project into a folder so that we can take a look at the source code. Now, a lot of this isn't necessary for understanding the code. For instance, demo videos, launch files that are used to run the demo project. What we're most interested in is this rosasummit.py file. This contains all the actual logic that we need. So first, we take a quick look and we can see that it's using LangChain and it's using Rosa. Now, LangChain is a Python library that is used to connect to LLMs. Rosa is a layer on top of LangChain. What it does is allow LLMs to talk to ROS-based robots. So this is what gives us the functionality like listening to command vel and summarizing what messages are sent on it. It also is the tool that allows us to plug in our own tools so that we can extend the functionality of Rosa. So let's take a look at how it's set up. In the main function, a number of publishers are produced, and we'll see these in the tools, so don't worry too much about that. We do our normal ROS2 setup to initialize a node, and then we create the connection to the Anthropic API with Claude. First, it reads the API key from the file, which is why we saved it to the file before building the Docker image. That means the API key is contained within the Docker image. It then uses that API key to connect to Chat Anthropic, and this is imported from LangChain. So now our LLM object contains a connection to the Claude LLM. The next step is that we want to set up a prompt, and here our prompt is, you are a helpful robot named Summit, designed to assist users in a simulated environment. You can navigate, explore, and interact with the environment using various tools. We then also list all of the tools available. This is where Rosa comes in. This is JPL Rosa, and what we're doing is constructing the agent which connects to the LLM and has a number of tools plugged into it, which are defined above this in the code. And we'll take a look at those next. It also defines different prompts, and because we only have one prompt, which is this one, that is what is passed to the LLM. So for now, every request that we make of the LLM, it is given this as an initial starting point. So it knows that it's trying to help, it knows it's in a simulated environment, and so on. Even without the tools, we get a good amount of functionality. But adding tools is where we start to add a lot more flexibility. So let's take a look at one of the simplest tools, which is the stop tool. Every function that can be used by the LLM is marked with the @tool decorator, and this is from LangChain again. The LLM is able to call this function directly. We don't need to give it permission. We've told it this is where the function is. You can go ahead and call it. And what the stop function does is it publishes an empty message to the velocity publisher. An empty message just means all zeros, which means move at 0 speed. So by doing this, it will move the robot at no speed, which stops it. But the key part here is that every one of these tools returns a string. The string is used to tell the LLM some feedback about what happened. Of course, LLMs are good at interpreting text, interpreting human language, which means that we can return strings with human language of what happened. We can say robot stopped, and that tells the LLM that the robot was successfully stopped because we've published this 0 speed message. This kind of tool format continues with other functions like toggle auto exploration. So true or false to explore or not. What we're going to do is construct a ROS2 message, publish it on the explore publisher, which talks to the nav2 library. And if we are exploring, then say that it started or resumed. And if we stopped exploring, then we've stopped or paused it. So the LLM can call our functions with particular arguments, and the type of argument tells it how to use the tool. And then it's returning a string of what the result of that function call is. We can see again, navigate to pose. It's given positions and orientations where it publishes a message. Navigate relative, it's given position and orientation relative to the robot. and all of the tools have this kind of format. SaveMap is a bit special because it doesn't produce a message and publish it like the other ones do. Instead, it's got custom code in where it saves the file to a particular location on disk. So what we've seen across these tools is that it can take 0 or more arguments. It always returns a string of what happened when it called the function. And within the function, normally we would publish a ROS message to make something happen on our robot, but we can also just run any arbitrary code we want. And that's what makes this really flexible. We can run any code we want, and not only is it, and because we're giving the LLM access to run it directly, we don't need to interact with it directly ourselves. We can give a high-level action, and the LLM can understand which tools it needs and how to break down the task in order to make that high-level action happen. So we've seen that we can use an LLM to control a robot using natural language. By supplementing Claude by Anthropic with some extra tools that we've defined in our code and the JPL Rosa library, we can add extra functionality and control our robot with natural language commands. Unfortunately, this is only possible by having a reliable network connection, but if your robot is operating in an area with a reliable network connection, that shouldn't be an issue. We showed the gazebo simulation with the robot responding to those commands. We also saw how to set up the simulation and went through the code to see how those extra tools used by the LLM are defined. So now here's my challenge to you. First, get the project running for yourself. See what kind of commands you can issue to the LLM and what it stops understanding. How can you break it? Then, once you've had a good play with that, see if you can add extra tools to improve the functionality of the robots. Remember that because of the Rosa library, Claude has access to all of the data that is being transmitted on the robot, including image data and LiDAR data. So figure out what you can do with this data and improve that robot's capabilities.